All right, well, thank you very much, Jorge. I appreciate the introduction, and I want to thank the organizers for putting this together, and particularly Tammy. She seems to have escaped the room, but we all know that as organizers, there's somebody doing a lot of the detailed work in the background, and we always appreciate that. So today I'm going to talk about dynamic routing for same-day delivery, and we heard a little bit about this on day one from Patrick, based on the work that they had done in the DIMACS NeurIPS challenge. I also participated in that challenge, but we came in 6th, so I figured I would talk about something different. So, but I did take some solace in the fact that listening to Patrick's talk, one of the keys and what we also focused on was how do you kind of get some quick way of costing those customers that, to determine who should go in the first wave and who gets, who waits until the second wave. It's just they did a really, really good job of it. So congratulations to Axel and Patrick for the work that they did there. That was excellent. So I'm going to talk about same-day delivery, but I'm going to kind of talk about a different aspect of that. And I think one of the places I wanted to start is that, I think over the last year there has been, layoffs and, companies that are backing out of warehouse contracts and so on after the pandemic, and some thought that maybe last mile delivery has been dying. Well, the truth was that there was just that massive acceleration that came from the pandemic. And if you look at the data, the trend line, what you can see now is that top blue line which is in 2022 dollars, right? It's just now we're about on trend with where we were previously. So the market is still quite healthy, and as all of you probably know, there are all kinds of players and different business models that have really emerged in this space, whether it's Amazon or somebody like Postmates who's shopping in stores, the way that Target manages this out of their existing stores, similar to Walmart. There's the grocery side of the delivery, and then also the meal delivery that has really exploded through companies, at least in North America, like Grubhub. So my interest today, though, is more on that goods delivery from a single depot, something like you would experience through Amazon Prime Now, and I'm fully expecting at the end of this that all of the Amazon people in the audience are going to tell me this isn't at all how this works, and that would be great. Tell me that. But I think there's some interesting aspects here that I want to touch on. So for those of you who aren't familiar with these kinds of problems, so essentially we have this central depot that is going to serve demand. And one of the challenges of this that differentiates it, for instance, from the last mile work that we just heard about, is that the requests that are going to be served are coming in over the course of the day. So when we start that operation for the day, we don't know all of the requests that are going to need to be served. So when that first request comes in, right, you have to make a decision. Do I serve that request, or do I wait and accumulate requests for to get some consolidation for the delivery? And so that becomes one of the key, right, the key question that you're asking. And so in this particular context, I'm going to change the problem a little bit from what was in that DIMACS NeurIPS challenge. And one, in this talk, I'm not going to focus on minimizing delivery tour time. Rather, what I'm seeking to do is make decisions that allow me to maximize the expected number of customers that are served. And I think this has been a debate that has run in the dynamic routing community, in that question of whether or not you are really trying to minimize, as we do in traditional routing problems, that distance or time, or whether what you really want to do is maximize who you can serve. So what I'm going to argue is you maximize who you're going to serve. This is maximizing revenue, and that because implicit in there, when you have a time dimension, and in these particular problems, you have two of those. One, customers all have a deadline by which they need to be served, and you also have a length of the day. So when you have that constraint, that's a resource that you need to use efficiently and effectively. And so you're implicitly going to want to optimize the tour time if you do that. But in this context, then you are not required to serve all customers. So how does that work, right? There's essentially what happens is those customers are just generally not going to be offered a same-day delivery option in this context. So they come to the website, they just don't see that option for them because for whatever reason, right, and we'll talk about what those are, they're just not a good candidate for that. So I'm showing you one vehicle here because it's easier, but these are fleets of vehicles. And in contrast to the challenge that was discussed on Monday, I'm going to assume that you can dispatch at any time rather than using the waves model that exists. So implicitly as well, there becomes this decision about when should I, after a vehicle returns, when should I dispatch again? So most of the work I've done would show that generally you're dispatching as fast as you can after that vehicle returns, and that there's not a whole lot of value in waiting at the depot to accumulate more value. So as I said, we have this problem, we made that decision, the next request arrives, and in fact, while we do that route, more requests are arriving. We're planning a route for the future, and that's the route that we will execute when we return. And then at some point in the future, you get this request, and one of the things that happens, as I mentioned, is we can't necessarily serve that request. And basically what's happened is it becomes infeasible because they all have time windows on them or time deadlines on them. You simply can't do it. You don't have the resources to do it. Or the other thing that's happening, if you are anticipating the future, if you're anticipating the fact that there are going to be future orders, even if you don't know what they are, you would often want to preserve some resource, and there become those customers for which the opportunity cost of serving them is high. That means that they're going to consume so much resource that it's going to limit the number of other customers that you can serve. So you might say, look, I'm just not going to serve that customer. And in other work that we've done, one of the things that happens, and you can see that here, so in this particular case, we were looking at mixed fleets of drones and vehicles, and we were really just sort of interested in who would you serve with a drone and who would you serve with a vehicle. But if we look at the travel time of the vehicle versus the course of the day, what you can see with these X's is you get to a point in the day where there just isn't enough resource to be serving, right? Early in the day, you have resources, but at a certain point, you've committed, and these folks that are calling later in the day, you just don't have the resources to serve them. Or in some of these cases, you're actually making decisions not to serve them, to preserve resources because you want to, you can capture a whole bunch of these closer calls. So, yes?
So, I'm just trying to understand the problem.
Sure.
Do the vehicles have capacities, and you're trying, what's the decision? I mean, why not just send it away? Why would you want to keep it? Is it because you can put more stuff in it and save?
Right, so then you can get greater consolidation on the vehicle, and so that, the cost per stop becomes less. Okay. But the trade-off, and we'll talk more about it, but the trade-off becomes, do I do work or do I wait, right? And so this is the classical trade-off that happens in these dynamic vehicle routing problems, particularly same-day delivery problems. But there are capacities, right? You see an Amazon truck, it does have a capacity, but in a same-day delivery context, your routes tend to be really, really short. And so that's generally not the issue that's impacting you.
So these X's would be like an Amazon where Flex would come in?
Yeah, so that would be an opportunity to use Flex in that context, or again, as I said, you're simply not showing them you're not showing that option to the customer when they come. But Flex, that crowdsourced delivery would be the other way that companies, Walmarts and Amazons are handling that. So the question that we started to ask after we saw this was, if there are these sets of customers or regions of customers that find themselves being unserved, right? Even if you have an option like Flex, there are going to be customers that end up being unserved. So then there becomes this question of how does that affect the demand that you face from your customers over time? And this kind of goes historically, and I'll get into this as we think about how we model these problems, right? We tend to focus on optimization for the single day. So we wanted to look at something where we could draw some insight, and we said, okay, let's do something simple. Let's assume we have two regions of equal size, but the second region, the region on the right, has relatively more demand than the region on the left. So what then happens if you're optimizing for the day and you make that demand dependent on the level of service that the region is experiencing, right? You can create scenarios where you get really bad outcomes where essentially the demand in that first region gets driven down essentially to zero because you never serve it, because you focus on the higher demand region because that's where the density is, that's where the consolidation is, that's where the less expensive per stop delivery is. So you essentially start moving away from serving that less, populous region, and you get these scenarios. Now I created this because it's a bit extreme, but it does raise the question of, for our ability then, over the long term to kind of maximize revenue, maximize the number of customers we're serving, do we need to be thinking differently than simply our traditional daily optimization problem in these dynamic settings? So, we talked a lot about deterministic routing. I think everybody's really familiar with that. The problem I'm talking about is a stochastic sequential decision-making problem. I and Warren Powell, who I think clearly has more clout than me, would argue the way that we model these, or the best way to model these, is a Markov decision process. And Warren is taking to calling these sequential analytics. And essentially what we have is we have a state. This is what we know about the world at this moment. We need to make a decision. This puts us in a post-decision state. Those of you familiar with Q-learning is finding the value of a post-decision state. And then we have a random transition. In this particular topic, what I'm talking about in that random transition is who else is requesting service, right? And we experience that transition, and we transition to a new state. So the solution to one of these is what we call a policy. And what we're seeking, and sorry, I think you go from a Mac to Windows, it moves things around. So we're seeking the best policy that's going to maximize that expected value. In this case, we're earning a reward for serving a customer, so we want to maximize the expected number of customers we serve. And probably everybody's, right? And so there you have the state, you have a decision given by the policy when you're in that state. And what people often think of when they think of these MDPs is they immediately go to the value function or the Bellman equation. I want to emphasize that a Bellman equation is a consequence of the model. It is not in and of itself a Markov decision process model. But what we do know, right, is that an optimal policy under certain conditions, which are almost always hold, right, is going to be satisfied by this Bellman equation. So we use that, right, in order to solve these problems. So I'll just deviate a little bit, and Jorge and I were talking about this yesterday. There was a period of time where I would go to conferences and literally be the only person that would talk about dynamic vehicle routing. My introduction to this came in 1997. I was working for a company called Schneider Logistics, which was a subsidiary of Schneider Trucking, which at the time, and maybe still is, at least the largest truckload carrier in North America. And we were looking at cases where we had freight that we were moving across the country. In fact, at that time, we were moving it for Caterpillar from Atlanta up to Peoria. And we had a lot of capacity left in the end of our trailers. And so we were looking at ways that we could make use of the extra capacity that we had. And we started talking about the possibility that we would make stops along the way and maybe pick packages up. Well, as it turned out, the shortest path between the Atlanta suburbs and Peoria didn't have a whole lot of opportunities for picking up freight. And so what we started looking at, and what eventually became my dissertation, was looking at how would you change that path in anticipation that you might pick up freight from other places along the way. And so that's how I got into this. At the time, there just weren't a whole lot of folks working on this. And the original, and still you see this in the literature, but the original way of doing this was focused on re-optimization. And basically what that meant is that we would re-solve the problem for each state that we encountered. And in essence, what that would do is you would set this cost to go term to zero. And it's perfectly rational, particularly coming out of everything that we've heard here, because we're really, really good at solving those deterministic routing problems. So that made a lot of sense. The problem that can occur is that this matters, right? That if you don't account for the fact that the decision you make today impacts the resources you have available to do work in the future, you are going to get relatively worse solutions than you would if you considered that. So there becomes this trade-off between all of this technology that we have to solve routing problems and the fact that these problems have an additional term associated with them. So, but the beauty of this, of course, is it also overcomes the curse, one of the curses of dimensionality, which is the state space, right? All of the problems that we deal with when you have a routing problem is it's a combinatorial optimization problem, as everybody here knows. And so, right, the state space is, massive, billions, trillions of states. Even when you're considering, single vehicles, you end up with billions and billions of states. So this isn't, it isn't crazy, particularly if you go back to the 80s and 90s when computing power couldn't do much for us. And if you're really interested in this kind of a little bit more context on this, Florine Hildebrandt, Marlon Umer, and I wrote a paper that's now in Computers and Operations Research as we sort of try to connect that history up to the point of machine learning. But as I said, it ignores the future. So the next obvious thing is to do what we call look ahead or rollout approaches. And as people in here know, I'm very fond of rollout approaches. They have some really nice theory associated with them. But the simplest form of this look ahead is that we're going to look ahead and look into the future, but we're only going to look one time step into the future. We're only going to look forward to the next decision, because then it really dramatically reduces right? The number of things we need to consider makes it more tractable. The beauty of these look-aheads is they also have that, they only solve for realized states, so we're reducing that curse of dimensionality. But again, you're looking one step ahead. Or if you roll out, you can look all the way to the end of the horizon, but now these things are happening online, and that, again, starts to become really computationally expensive. So, what do we want to do? Well, this is where, obviously, deep learning has been, kind of powerful because it really, I think for all intents and purposes, has removed the question of the state space dimensionality, because we can, for the most part, right, we're able to derive feature sets that are enormously large, and there doesn't seem to be much, particularly in modern computing infrastructure, we don't seem to have that kind of state space dimensionality problem. And so then you have, we can solve for sort of approximate, future value. Oh, I needed to change that. That should be the sum there, sorry. Or, we've talked a little bit about policy gradient methods, right, where we solve directly for the policy. Now, in these two instances, one of the problems you become now is that as we've already mentioned, we're cursed by the action space. So if you think about a policy gradient, I need to enumerate the actions. I can't do that for these problems. The combinatorics, it's totally impossible, right? So now you have this problem of the action space, and this was alluded to by Patrick in his talk. We end up with this decomposition, right? First, in their case, who do we serve? And then what are the routes that we use to serve them? So we're going to do the exact same thing here for the moment, and partly because we first started working on some of this before any of the sort of transformer models came out, and so we need to transition too. I think transformers are probably the answer here, but I've got to go back and do a whole lot of reading, because I conceptually know, but I don't think let's be honest, I'm never going to implement it. I'm going to have to have somebody do that for me, but at this point in my career. But I think that's what we need to do. But in this particular case, what we're going to do is, you guys are going to learn this. There's so many students here, but eventually you're going to get old and you don't code that much anymore. It's just what happens. So.
This takes really long.
Or it takes really long because you have to Google everything, so you don't remember the syntax anymore. I don't know, maybe Copilot or ChatGPT is going to fix that for us. We'll see. But anyway, so what I'm going to do here is decompose the decisions. So we're going to decompose this into, first, this acceptance or rejection decision, as well as a decision about which vehicle that we're going to use. And so these, right now, I've just massively reduced the action space. And so I can do this with either Q-learning or policy gradient. We use Q-learning in this case. And then we're going to use a heuristic outside of the reinforcement learning to do the routing. So as I said, I think there's opportunity here to do this with transformers, and I think probably some of you may even be thinking of that. If you're not, I encourage you to do dynamic routing. I'd love to see more work in this space. And so, as I mentioned now, so when we're solving these daily optimization problems, well, what I wanted to look at is what happens over 2 years. So we're going to implement Q-learning as I described. We'll have region 1 that has less demand initially than region 2. Demand will evolve over time. The first example I showed you was really extreme because I wanted to show you what can happen, particularly if you don't have enough resources and you really have to make changes. But here, we'll assume that we have enough resources. That is, we have enough vehicles and enough time in the day to serve 80% of the demand, at least 80% on average in both regions, right? And so if we do that, you can see we get 268.9 services on average between these two regions over the 2 years. And so here we get to kind of this other question that arises often in dynamic routing, and I will say this is probably the most frequent thing that I have been asked by reviewers over a 20-ish year career now, and that is, what is the optimality gap? Well, the truth is I don't know, right? That's one issue in all of this work is that, right, you can't just use, say, supervised learning because I don't even know what the solutions are supposed to look like. I could do perfect information, but most of these problems are so big I can't even solve that exactly, even with modern techniques. So I don't actually know what the optimal policy is at all. And so that becomes a really big challenge. Now, Jorge has done some nice work with Nick where they used information relaxations. Those are, I think they're fascinating, and it's a really interesting direction, but I think Jorge will admit you still can't solve very large information relaxation.
We did 5 nodes.
5 nodes, right? So they solve 5 nodes. I mean, so I love the idea, but it's not there yet where we're going to be able to bound everything. So then we started to ask, well, what would a good solution to this look like? What would you expect to happen if you were in a steady state that was optimal? And so we kind of looked at, let's kind of come up with some model that might be what that steady state would look like. And so we said, okay, we're going to maximize the sum of demand in each region. So R is going to be kind of the fraction of demand that we serve in a region, and lambda will be the demand in that region. Now remember, this is constrained. We're constrained by time. We consume resources. So what we did is we wanted to approximate in a continuous way the consumption of resources. So we used the Beardwood-Halton-Hammersley approximation, right? So here's N from what Bill was showing yesterday, and then A would be the area. And as I said, we're using exactly the same areas here. And there's the constant beta. And then again, demand is endogenous. It depends on the rate at which you are serving customers in a particular region. So we took this, and it turns out that you can kind of reduce this and get an understanding of what can happen. And what you see, right, is that the demand that is being served equalizes between these regions. So we want to be on a given day, as I showed you, you don't necessarily optimize over the 2 regions, right? Try to balance that out. But over time, in fact, that is what you would want to happen. And so we wanted to use this information to see what we could do. So the first thing we did, here's the original, was train, right? We wanted to incorporate that information into training, and we said, okay, let's train on much more diverse data that represents not only the evolution, but represents what we want to achieve. And then we also had a few model-aware features. And you can see that doesn't get it there. But in this particular case, I don't know, maybe it was having more robust training, right? And so I think from the computer science side, you would have thought of that immediately, right? You would have just, oh yes, of course you're going to do more robust training. Coming from the OR side though, right, we start with that Markov decision process, and historically you would fix a set of transition probabilities. So from that sense, it wasn't odd what we did, at least coming from that direction. But now we've changed that, and you can see we get much more, we're serving more demand on average, but now we clearly haven't, the structure should be converging, and it's not. We've gone the other way. And so the question is okay, maybe our model was wrong. It was an approximate model. Or maybe we need to do something else. So the thing that we did is we looked here. And we looked at the fact that you had these ratios. And what we then did was we said, all right, we're going to augment the reward function. And we're going to use the ratio that we're achieving as an augmentation of the reward. So we're essentially going to give more reward for serving the underserved region, and we're going to do that proportional to the demand that's being served in each region. And when we do that, right, we actually get, again, a little bit more, and now you start to see the convergence is starting to happen there again. So it turns out that we could exploit what we had learned in our steady state model. We exploited that information to augment the reward in the learning phase, and that led us to, then on that, as we tested that, that led us to the performance, like better performance, and now you can see it's starting to converge to what the steady state model suggested would be closer to the optimal solution. So, you know, as I look at this, again, not the most sophisticated machine learning by any sense, but that machine learning has given us an opportunity to, I think, solve problems that historically, these dynamic problems have been very difficult to solve. We've been very limited in our ability to solve them. And now opening up these other questions that we haven't explored in the past as we think about kind of the scope of the operation that's taking place. So I'm pretty sure I'm right around the end of time there, and I'll stop there, and I don't know if we have any time for questions, but be happy to take them.
Time for one quick question.
Well, let me encourage you all to work on dynamic problems, but
The one point that I didn't quite catch as a start was same-day delivery,
yes.
and then you came to this multiple-day period.
Right. So, yeah, I probably glossed over this. So we're assuming that the deliveries are happening over the course of a day, but you know that operation is repeating day over day. So what we
But if you don't serve a customer on day one, he probably has no interest to be served at day two, or are you assuming that he will come back?
no, well, they might not come back, and that's kind of the point of the endogenous demand function, is that they might not come back, right, if we don't serve them. And the other thing I didn't mention, because Jorge was giving me the 5 minutes and I knew we needed to stop, was that we tried to train this considering a multi-day horizon, but there was just so much variance then at that point in the training. We just weren't getting anything. And so what we tried to do was manipulate the training of the daily optimization problem to get outcomes that were good over the long term. So that might have helped, and I missed that context. Yeah.
So I'm sitting here wondering about the next level model that has this region full of college students. So
Yeah.
It doesn't really spend very much money. Over here's the city where
Mhm.
rich people live. And, in other words, you're getting different value from different
Yeah.
types of customers. And it could mean that no one's ever going to serve the students ever again.
Well, and so that's a potential outcome, but if you think about that college student 20 years from now, right, you don't necessarily, you know, like in the today, yeah, there's less revenue there because who knows, they're ordering Pop-Tarts or something, right? But in the future, right, those are the consumer that you want to have when they're 40 and 50 and 60. And so, you know, this kind of does get at that point as well. And then there's also within this, right, there become questions of, you know, sort of bias in who you're serving, right? Because it might not be college students, it might be low-income neighborhoods. And, you know, one of the other papers we worked on that was actually what led to this was thinking about the pandemic, that you had populations that needed to be served in these ways that might have traditionally been marginalized, or certainly our algorithms would be biased against them in the ways that I showed, right? Because they don't spend as much. And so how would we manipulate our algorithms to make sure that you're also serving those otherwise underserved populations? So I think that becomes, that is also an important element of this discussion. So you're right about that. Yeah.
One thing that I was curious is the sort of time frame that we're looking at, because there's going to be convergence, but how long do you think this convergence will need to take place?
Yeah, so we did, you know, we've looked at a year, we've looked at 12 months, we looked at 2 years, which is what you're seeing here, to actually see this convergence. I suspect that's too long in an operation. I think the demand models are changing probably more rapidly in ways that there's exogenous factors to the demand model I'm showing, right? I mean, areas are growing, areas are shrinking, there's macroeconomic conditions, there's sort of other things that impact this that you're right, we didn't consider. And so I think here what I really wanted to do was kind of grab that insight that this actually happens when we are focused on optimizing for the daily and try to draw some insight. I think the real problem is much more complicated. I would absolutely agree with that.
Any other questions?
Okay.
Thank you very much.
Thank you.